let's start off with the average student data. We've looked at before. And this should be in your recent Google Drive, but I'm going to share my version of it with everyone right now. Remember, when we share a Google document, we want to make sure that the get link has anyone on the internet can view this when you put this in a submission, so that way I can read it when you send it to me, or you can read it when I send it to you. If it's not, you need to go in there and make sure it's set to anyone with a link and not restricted or set to a specific organization. Copy. So if you check out the chat, I'll post this link if you want to play along with me. All right. So there it is in the chat. So let's play with, how about height? And just for fun, for comparison, I'm going to attach it to gender. So I'm going to make new tab here. So if you're going to make a copy, hold on just a sec till I sort this out. Don't make your copy quite yet. So I'm going to grab the genders, which we'll look at in a little bit. And then let's copy that in here. And then I want the heights. And don't quite make your copy yet. We need to see if we got to clean this up a little bit. It's always a good idea if you have multiple tabs to label them. So if you just double click on the tab at the bottom, we can give it a better name. Let's just call it height for now. Better. And then whenever we sort data, you should always highlight the header row, especially if there's more than one thing. And that looks like the bottom of it. And thank you all for those of you who did fill out this survey. So we have data to play with about y'all. And from data, I don't want any of the first few options. I want to be a little more particular about my sort. I want to use just sort range, and then I don't want it, yeah, I guess we could do by gender first. So that's fine. And then we'll also sort the genders by height, smallest to largest. That should be okay. And sort. All right. So we just want to look for any weird stuff before we start trying to summarize and graph it. Okay, so there's a few confused males, 5 inches tall, 5 inches tall. Okay, so they didn't quite read, oh, sorry, a few confused females. They didn't quite read the directions there. So those are going to have to go. So we're just going to pull those out because I don't know what they meant by that. Did they mean 5 feet? Or did they just mistype? So let's delete them. Delete those rows. Yeah, and let's see. Confused males. Where are the males? There we go. We have a blank female. We should pull that. And then, okay, so it just looks like we have some typos on the female data. And then we have a blank. We'll pull that out too. Row, please. Okay, so now this is ready for us to play with. Tighten this up a bit. So what I'm going to do first is I'm just going to calculate all the summary statistics, and then we'll play with them. I'm just going to put a title up at the top here, summary statistics, and we'll look at the formulas we need for each one. So count is something you should always do first. That's our N, and command in the program is just called count, and then highlight the data. Now for this data right here, since I only have the title and the numbers in that column, I can just select the column as opposed to dragging through the specific cells. And then we can reuse this. I do not want to autofill, thank you very much. All right, next thing I want is the mean. And on the spreadsheet, the mean is called the average, and there's a bunch of different ones. We just want the one called average. Column B in this case, close your parentheses. Next, I want the standard deviation. I'm going to call that just STDV, standard deviation. And there's a bunch of different ones. So if you start typing STD, then you should see there's STDEV, that one's good, STDEVA, P, and .S. So .S is the one I recommend. It actually works the same as DEV, But if I'm going to bring this over, if I'm going to send this to anybody that uses Excel, Excel would like the .s one better. So we're going to use the .s for sample. That's important. Standard deviation of a population is different than standard deviation of a sample. We have to differentiate. Otherwise, we get the wrong number. Add that to the notes. So for standard deviation here, spreadsheet formula is STDE dot S, and then we highlight where our data is. Average here, mean is average. So and then your data. Okay, let's go back here. All right, so usually I just block these two together because they're related. You cannot have a standard deviation without the mean. So when the computer calculates the standard deviation, it's calculating the mean first, even if I didn't, it has to. I'm gonna skip a row there and come down for the percentiles. So for the percentiles, I usually put them in the order of the 5-number summary. So I want the minimum, I want Q1 next, I want the median, and then Q3, and the max. So I like to put those in order next. So min, pretty straightforward, command is min. And then in this case, it's safe to click on the column. I always question whether that's safe. And basically, is there anything else in that column that might mess that up? So if there are any other numbers besides that data, then I wouldn't click on the column. I'd have to highlight the individual numbers. Quartiles. So here we have the quartile command, quartile exclusive, quartile inclusive. So in Sheets, quartile and quartile inclusive are the same. If I was going to send this to somebody that uses Excel, they would appreciate the quartile inclusive instead. So I'm going to go for that one, but it does the same thing as quartile. We'll never use quartile exclusive. So pretty straightforward data, but this time it wants to know which quartile I want, 0, 1, 2, 3, or 4. And so I want the first one here. I got to tell it that. Also, median, just median data, quartile 3, like quartile 1, we'll use the quartile inclusive. We will never use quartile exclusive. Data, this time I want to say comma, I want the third quartile. So that marks the end of the third quarter. And we'll talk more about the difference between a quarter and a quartile later, once we graph those. And then the max, it is just max data. And then so these are the general statistics I need when I'm analyzing a set of data. There's a couple more we'll calculate. We'll get to those later. Like other ones we'll calculate later. Our range, IQR. Range is pretty straightforward. I talked about that before. IQR we'll get to the second part of class today. So I just want to go back over some things I mentioned about the min and the quartiles. So all of these are also percentiles. And I mentioned earlier the minimum could be considered the 0 quartile or the 0 percentile. So I'm just going to double check that by using the quartile command. So if I say, hey, what's the 0 quartile? So what marks the place where there's nothing below? Well, that has to be the minimum. Alternatively, I can bring up the percentile command, and there's a whole bunch of those. So either percentile or percentile inclusive. Percentile rank is like a backwards lookup. We're not going to do that in this class. So I'm going to go for percentile inclusive data, 0. And here they want a decimal version. So we'll see that again in a second. Let's pick on quartile 1. So quartile 1, that marks the end of the first quarter. So 25% of the data should be at that point. So if we try the same thing with the percentile command, which is either percentile or percentile inclusive, they behave the same. Data, comma. Now notice down here, they want a decimal for the percent, first quarter ends the first 25%, so it ends with 0.25 for that percentile. Notice I get the same exact number. A thing about quartiles and percentiles, in the world of mathematics, the world in general, there are more than one ways to pick which number marks that. And the reason is, if there's exactly 100 numbers in the data set, it's pretty easy, but there's always more or less than 100. It makes it a little trickier to pick which number. My point is, if you have a TI calculator, it picks differently, so you won't get the same number as a spreadsheet. If we use stat key, it picks slightly different, so we won't get exactly the same number in stat key. And there's some by hand methods that I introduced in the homework. We'll go over one of those today. It picks a slightly different number. They're all in the ballpark of each other, right? So one might say it's 63, the other might say quartile 1 is 64.5. This one says it's 64. They're close. It's not a huge deal. So if when you're playing with the homework with quartiles or percentiles, you're having trouble getting the number the computer wanted, message me on that question and I'll try to explain what was going on there. So, warning, there is no uniform way in the world to calculate a quartile or a percentile. So some computer programs will do something different. All right, hang on 1 second. And let's just do median a little more for fun. I use the median command here, right? So I'm just going to compare it to the quartile command. So median marks the place where 50% of the data is below. So that can, okay, good, thank you. That could be either the quartile 2 or percentile 0.5 for 50%. So let's just double check that's true. I'm not just making stuff up. Quartile inclusive data, comma, second quartile, which is the end of the second quarter. 67, same number, versus the percentile command. Remember, we'll never use the exclusive versions of these commands in this class. And then 50th percentile, it's 50 out of 100, which reduces down to 0.5, half, right? Okay, so usually I do the commands the way I did here, which is min quartile inclusive 1, median quartile inclusive 3, and max is just max. But there are some times where I choose to use the quartile command for all of these. So you might see that in some spreadsheets I share. And again, we'll try to get used to these ideas a little more. Other things to consider. Often the percentiles will come out to be like the data if the data was whole numbers, but sometimes some rounding has to happen in the way they're calculated, like the median. I often have to average the middle two numbers so I could get a decimal version. The mean and the standard deviation will almost always be these crazy decimals out there. And the rule there is always round to one more decimal place than the data. One person entered 1/10 of an inch. Another person entered 1/10 of an inch, another person entered 1/10 of an inch. So then my summary statistics, if they need to be rounded, should be rounded to the nearest 100th. So we go one more decimal place than the data is the usual rounding rule in statistics. So let's just drop those down. All right. Next thing we're going to take a look at is a graph of the data. So I want to show graphically what the mean and the standard deviation mean, and graphically I want to compare the mean to the standard deviation. So we're going to make a histogram. Let's just use the quick histogram builder. So we just highlight the data, and then over insert chart. Usually Google will pick histogram. Instead it picked the crazy pie chart. That's beautiful. That's not what I want. So then I look for histogram. All right, so I made that histogram and it's got some funky endpoint numbers. So I just want to pick something nicer. Let's see, 50, 52.73. So it's jumping by almost 3. So usually the next thing I do is edit those numbers. So that's under customize histogram. And I don't want the auto. Let's see what 3 should look pretty similar to that. It's not too bad. and just kind of play around. There's no best histogram, right? So we just got to kind of find one that is good for us. I think I like the 3 better, but I could try 4 for fun. That's not too bad. Let's see, before I decide what is, the mean is 66, the standard deviation is 4.25. I'm going to go based on that. I'm going to go with the 4 because it's similar to the standard deviation, and it's going to help me, I think, explain what standard deviation means. All right, so I'm just going to pull that over. So I chose my bucket size to be 4, starting at 50. And I have 1, 2, 3, 4, 5, 6, 7, 8 columns, 8 buckets, bins, classes. There's lots of names for them. Remember, when you use a quick histogram builder like StatKey or Google Sheets, Microsoft Excel, there's a ton of others out there, they usually count so that the lower number of any group is in that group. So 62 is in this second tallest column. 66, if somebody has that height, would be in this tallest column here. 70, if anyone has a height of 70, they end up in this third tallest column over there. So just something to keep in mind and how those counts work. Slightly better titles. Let's see, how about student heights? Height in inches is good. And then this is a frequency histogram. So these numbers on the side are frequencies. Frequency means count. What are we counting? We should be specific. The best title here, I think, would be number of students. Students. There we go. All right, so we got a good graph. Let us now draw on the graph to try and figure out what some of these summary statistics mean. First, does anyone see a skew here? It looks symmetric, skewed left, skewed right. How would we describe this graph to somebody?
It's pretty symmetric, but it might be skewed a little to the left.
Yeah, that's what I think too. Yeah, it's got a pretty symmetric bell shape here, but there's a little bit of a tail on the left there. So that's what I would think too. Good observation. All right, let's play with it. So I have the luck of having this digital board I can copy stuff to. If you're writing this down in your notes, I would just try to make a quick sketch of this with rough heights, scaling the axis 50, 54, 58, 62, 66. And then I also want to see my summary statistics. Copy most of these. There to look at. And same page. Okay, so first thing I'm going to do on my histogram is I need a sketch on paper. So whenever possible, do that. And I'm just going to label the mean on here. So 66.49. So here's 66. There's 70. That would be what, 60? There's 4 in between. So that mean is probably about right there. So that would be X bar. The median, 67, is over this way more, just a little bit to the right of that. So here is M, the median. So remember, the median gets the lowercase m, and the means symbol is X with a bar over it. And notice that the mean is a little bit to the left of the median, and that usually happens when data is skewed left. So just a note about this distribution. So this distribution is relatively symmetric. Right, it's got kind of a, if I draw lines through those like midpoints in a smoothish curve, it's got a relatively symmetric bell shape. It's relatively symmetric and bell shaped with a slight skew left. see, do I have my right and left to right today? Yes, got it. I often screw up left and right, so if I do in class, please correct me. Like last time, I appreciate that. Yeah, so again, the reason is when we calculate a mean, we have to use the actual numbers. So that min of 52 gets put into the calculation for X bar. But the median is just the middle number when the number is in order. It doesn't care how small the smallest number is or how big the biggest number is. It's just bang in the middle. So anytime we have a little bit of skewness, that's always going to pull the mean away from the median. All right, so next thing I wanted to take a look at is standard deviation. So standard deviation gets the letter S, lowercase s, and it's about 4. So just for purposes of graphing, I'm going to say the mean's about 66 and the standard deviation is about 4. So if somebody was 70 inches tall, right here, then they would be 1 standard deviation above the mean. So I'm just going to make a new axis down below here to talk about the standard deviation. And remember, what is standard deviation? It's a measure of average spread from the mean. Notice that some of these numbers are like right at 66 or pretty darn close, but others are pretty far away out here, okay? So they deviate more. The idea of deviation is how far is a particular number from the mean. So that's important. Deviation. X always means just some number in the data, like my X is 68. Somebody else's X might be 62 or 74. So if we take somebody's value and we subtract the mean from it, that's deviation, and deviation is just distance from the mean. Okay. So somebody that's 70 inches tall has a deviation of 4. So for example, if X equals 70, then the deviation for 70 would be just 70 minus 66, which is 4. On the other hand, if X was equal to, say, 58, then the deviation for 58, it's always the X value minus the mean, right? So that would be a -8, which means they're 8 below average, 4 above average. Sometimes people are just average. Sometimes people are above average or below average. It's not good nor bad, it's just the way it is. Okay. What standard deviation does is it just counts how many of these numbers, 4. So instead of counting by 1, we're counting by 4. So I'm gonna take this axis I drew a minute ago, and the mean is 0 deviation. It's right there in the middle. Okay? So we're using the mean for the middle, and then 70 is 1 standard deviation above average. 74 would be 2 standard deviations above average. 78 would be 3 standard deviations above average. So this axis I have here is an axis for S, the standard deviation. 0 is always the middle, as in the mean. 1 below 66 minus 4, that would be a -1 standard deviations. 58 would be -2 standard deviations. And we always count from the mean. This is super important with standard deviation. And this would be -3 standard deviations over there. So I'm just counting how many standard deviations these numbers are on each side. So although 70 has a deviation of 4, 70 is 1 standard deviation above the mean. a little about the way the computer calculates it. Now, as far as we're concerned, we're just going to push a button that says STDEV, and we're going to get a number. But where does that measure of average spread from the mean come from? And so it comes from deviations. So I'm just going to explain it by looking at the spreadsheet a little bit. I'm going to just copy that column into a new sheet for a second to screw around. So again, the idea of deviation is just distance from the mean. So for example, for 52, the deviation would be take that number 52 and subtract the average. So I'm just going to calculate the average on the fly here. So 52 has a deviation of negative 14-ish. So it's about 14 inches below average. Now I'm going to calculate all of the deviations by just filling this down. So every number has some distance from the mean. And since the mean, because we have to add them all up and divide, it's not usually a nice number in the data set. So our mean was about 66.5-ish. So that's right in between 66 and 67 here. So you can see that 66 has a deviation of about negative 1/2. 67 has a deviation of about positive 1/2, right? So if you're 67 inches tall, then you're about a ½ an inch taller than the average student, at least based on this sample. Let's clean those numbers. There's too many decimal places. It's hurting my head. Let's go with just one decimal place today. All right, so that's a little cleaner. So what I want to do is I want to know on average, how far are people from the mean? So it makes sense. So why not just add all these numbers up and then divide by how many? But here's the crazy thing about the idea of mean, and I'll explain this with a simpler example in a second. Yeah, when you're talking about standard deviation, you talk about positive or negative would be above or below respectively when we're writing about it. So we don't usually use the word negative. We just say it's above or it's below. All right, so if I were to add all of these up, right, sum the deviations, watch what happens. This is wicked cool. So I just use the sum command, which means add a bunch of stuff up, and I'm going to add all these guys up here. And it says 0. What the heck? So if I try to average the deviations directly, I'm going to get 0 because the sum of them is 0. So let's look at why that is, and then we'll move on and play with how we use this number. Just look at a much simpler data set. So let's take the numbers. How about 3, 4, 5, 6, and 7? So my daughter and her friends, they go out and they're going to get some pizza, and they all pull out their money to see what they have. So one of them had $3, one of them had $4, one of them had $5, one had 6, one had 7. Now 5 is the middle number. These numbers are equally spaced. So if you add these up and divide by 5, you're going to find that this is not only the median, it's also the average. So that's also the mean right there, right? So I'm just going to double check by making a sum here. So 7 and 3 and 7 is 10, 4 and 6 is another 10, plus 5 gives me 25. So then as far as the mean goes, it says take the sum, divide by how many? So that gives me 5. So they put their money on the table, they got 25 bucks to buy some pizza with. Now, another way to think about it, let's suppose on a different day they went out and they each had exactly $5. Right? This has the same sum. So it's also going to have the same average. The way to think about the mean average, it's the amount that you would redistribute from the sum so that everybody has the same. Everybody is average. Then you have the same total right there. So because of this physical aspect of what the mean, it's a redistribution of wealth, you could say, so that everybody has the same, but we have as a group the same sum. The deviations are always going to add to 0 because of the essence of the mean. So the trick people came up with to calculate standard deviation, again, standard deviation is a measure of average spread from the mean. So I'm just going to write that down again because this is important. This is like the intuitive definition of standard deviation. Standard deviation is a measure. There are other measures, but we only care about this one. Oops. Average. I use the word spread, but we could say distance from the mean. And because the deviations always add to 0 because of the essence of the mean, the trick is to do this, to find the deviation, which is x minus the mean. And to deal with that canceling out of above and below average, we square them. And so squaring them gets rid of the sign. After we square them, we then add them up. So now we get this non-zero sum. And when we're working with samples, normally with averages, we divide by n, the count. But for a sample standard deviation, we divide by n minus 1. So now this gives us an average of the square deviations. To get rid of the square, we take the square root after all of that is done. So find the deviation, square them, add them up, divide by n minus 1, then take the square root, and this is the number we call S, the sample standard deviation. You will never do this by hand. Well, you could, but I recommend don't do it. It's not worth your time. Just push the button, stdev.s, plug in your data. And then the computer will do all of that for you. Sample standard deviation. Okay, so essence of mean leads to this weird formula here, but it turns out this weird formula is super powerful. It's mathematically speaking the best way to find the average spread of the data. There are other ways, but we don't care about it. So I'm going to delete this chart. It's just for demonstration. Delete. All right, so let's go back here. Here. That's what I want. So deviation. I'm a deviant. I'm not average, right? I'm slightly above average. If the average is 66, I'm 68. I'm 2 inches above average, or about a half a standard deviation in this case. Interesting thing about this count of standard deviations, when we count by standard deviations, that's called a Z-score. You may have read about that in the book. So we count by the standard deviation, whatever number that is. So here I'm counting by 4. It's not exactly 4, but it's close enough for my graphical representation. So if I wanted to find my Z-score, right? If the mean is 66 and I'm 68, that's 2 above average. The standard deviation is 4, so I'm about half of a standard deviation. So if x equals 68, like for me, then my Z-score would be 1/2, because I'm a half of a standard deviation above average, it would be a plus. If somebody else had a standard deviation of, let's say, 58, a height of 58, then their Z-score, they are 2 standard deviations below average, so their Z-score would be -2. So a Z-score just means count by standard deviation. The formula for that is find the deviation, x minus x bar, and divide by the standard deviation. And again, all that does is count by standard deviations. So that's how we calculate Z-scores if we need them, and we do sometimes. Interesting thing about these standard deviations is that in general, when we look 2 standard deviations on one side and 2 standard deviations on the other side, we end up usually with about 95% of the data is in between. So usually about 95% of the measurements are within 2 standard deviations of the mean. Right, and we can kind of estimate that here. So about 58 is 2 standard deviations below. About 74 is 2 standard deviations above. So if I look at the data and say, okay, how many numbers are between 58 and 74? And I look at how many numbers are our total, I should find it's around 95%. Let's just double check to see that I'm not making stuff up there. Show desktop. All right, so I think I want the data actually sorted not by gender, but just by height. So let me redo that. So if I want to change that sort, I highlight all of the data, not the summary statistics. And then I just want to resort by height. So data, just the plain sort range. So I can say it has a header row and I can be selective about what I want to sort by. So this time I'm only going to sort by height. 52, 56, 57, 59, that looks good. And then I'm looking from 58 to 74. So if I just scroll through, 59 is the first number above 58. And then 74 is my cutoff. 2 standard deviations, and I'm going to include the 74s. All right, so I highlighted those numbers. If I go to the bottom right here, I can get a quick count. It counts 126 of them. So I'm just going to make a new statistic, let's say down here. So let's call this within 2 STDs. I found there were 126 of them within 2 STDs roughly. And there were how many? 133 numbers in the list. And that gives me about 95%, pretty close. So 90, if I round it to the nearest whole number, it's 95%. So this time I nailed it with this data set. Now it's not always going to be exactly, it could be like 90, it could be 99, but it's around 95 for most data sets. So I'm just going to summarize this in another picture. Let's see. Let's go here. So I'm just going to smooth out this histogram a little bit, make a rough sketch down here. So my histogram was roughly bell-shaped and kind of sort of symmetric. And in the middle of a histogram, we should find the mean. It's roughly in the middle, so that's my middle here. So that's my X bar. And then counting by standard deviations, right? This would be about 1 standard deviation, about 2, and about 3 would be over here. So 1, 2, 3. So that's a Z-score, which again counts STDs. Not sexually transmitted diseases, by the way. Standard deviations. And on the other side, if we look 1, 2, 3, so that would be a -1, -2 standard deviations, -3 standard deviations. My point is that if we look within 2 standard deviations of the mean, so I'm focusing on data that lives in the columns, these columns of my histogram here, I expect about 95% of the data. Sometimes this is referred to as the 95% rule. Or the 2 standard deviation rule. So 95%, that's most of whatever group I'm looking at. This is the usual crowd in here. So the numbers within 2 standard deviations right here are the usual suspects. Things outside of that are unusual. So if somebody has a measurement over here, they're unusually low compared to the rest. So these guys are unusually low numbers. And numbers over here on this side, more than 2 standard deviations to the right. So if your Z-score is 2.5 or 3 or 7, that happens sometimes, those numbers are unusually high. compared to the rest. These numbers are also referred to as outliers. Now, outliers aren't necessarily wrong or bad. They're just different than most of the other suspects that we have. They're not usual. Think about 95% in the middle. If the distribution of numbers is symmetric like this, then that means the tails have the split 5%. So if we cut 5% in half, that would mean that about 2.5% live in this tail. Oops, wrong tail. Data. And about 2.5% live in this one. And those are the unusual ones. We don't see those people very often, right? When you're walking around, you see a very tall person, you're like, my, that's a very tall person. But everyone else, you're like, eh, they're about the same height as me. Okay, so this is standard deviation. We can use standard deviation to identify numbers in the data that are outliers, unusual compared to the rest. Now, sometimes something is such an outlier, we gotta wonder, whoa, is that a mistake? Right, like remember, there was a 5 in the data set. We're like, well, that's a little too out of the usual suspects. And if somebody wrote they were 100 inches tall, we'd have to wonder about that. Say, I think that might be a mistake. Right? That's a little too far from the rest of the crowd. So standard deviation, super important. So next, we're just going to look at a few more data sets to play with this, and then we'll compare different populations and look at some of those percentiles.